Hello, mathematicians. I'm Aden Gonzales, and I'm a recently graduated high school math student working with Skew the Script on a few of the Algebra curriculum lessons. Today, we're going to be talking about the spread of disease, specifically COVID-19, and exponential growth. Let's skew it. Today, we're going to be talking about exponential growth and modeling disease. This is lesson 5.1 in our algebra course sequence. Specifically, we're going to be talking about COVID-19 or the coronavirus. The coronavirus pandemic was one of the deadliest pandemics the world has ever seen. And here's a video that shows the early timeline of COVID-19 in the United States.
The coronavirus has changed life as we know it across America. But how did we go from 0 cases to having more than any other country? The timeline starts on January 21st, when Washington State reports the first coronavirus case in the United States.
This is certainly not a moment for panic or high anxiety. It is a moment for vigilance.
Within a week, the CDC confirms Illinois, California, and Arizona also have cases. And on January 30th, Chicago witnesses the first person-to-person transmission in the country. February 17th, confirmed coronavirus cases in the US increased to 15. And by March 8th, confirmed US coronavirus cases reach the 500 mark. The World Health Organization then declares this 3 days later.
COVID-19 can be characterized as a pandemic.
And the next day, California issues a statewide stay-at-home order.
We are confident that the people of the state of California will abide by it.
Several states soon follow suit.
Stay at home.
Stay home, stay safe.
Quite simply, stay at home.
By March 23rd, New York has emerged as the epicenter of the outbreak with over 20,000 cases.
It's non-stop, literally. A lot of people come, they're not really survive, they expire.
So here's a timeline of a few key events in the early COVID-19 pandemic. On January 21st, we have our first case in the United States. A little less than a month after that, we have 15 cases in the United States. A few weeks after that, 500 cases. And then 2 weeks after that, 20,000 cases in New York alone. So far, more than 600,000 Americans have died from COVID-19. How did the COVID-19 pandemic escalate so quickly? That's what we'll be exploring today in today's key analysis. As always, you can follow along using the guided notes at the URL below. Let's talk about multiplication and exponential growth. Here's how viruses spread. We have an infected individual, and they spread it to 2 new people. On day 1, we have 2 new infections. Those 2 people each spread it to 2 new people. So on day 2, we have 4 new infections. Those 4 people spread it to 2 new people each. We have 8 new infections on day 3. On day 4, we have 16 new infections. And on day 5, we have 32 new infections. There's a pattern here in the number of new infections. We multiply by 2. Today's new infections are yesterday's number multiplied by 2. We can graph this exponential growth with our x being our days and our y being our number of new infections. Here's our axes with our x being our days and our y being our number of new infections. Here are our points from our table, and we can see this is the exponential growth. What happens to the number of new infections over time? We can see that as time goes on, the number of new infections goes up, the number of new infections increases. What happens to the rate of change in the number of new infections over time? We can see that at first, the growth is slow. The rate of change is small. As time goes on, the growth accelerates. Let's turn to real data. Here's the COVID-19 global case counts in the first few weeks of the pandemic from our world in data. We can see this, the exponential growth model is similar to our simple ×2 model. At first, the growth is slow, and slowly growth accelerates over time. And this is how the COVID-19 pandemic escalated so quickly. The statistician George E.P. Fox famously said, "All models are wrong, but some are useful." Although this model doesn't exactly fit every data value, explain why it may still be useful. And as a hint, think about making predictions. Now we're going to talk about modeling exponential growth. Remember, how viruses spread, the number of new infections is yesterday's new infections multiplied by 2. This repeated multiplication is exponents. Repeated multiplication by a number that's greater than 1 leads to exponential growth. Here we have our table. Our day 1, we have 2 new infections. We multiply that by 2 to get 4 new infections on day 2. multiply that by 2 to get 8, and again by 2 to get 16, and again by 2 to get 32. On day 1, we have 2 once. On day 2, we have 2 multiplied by itself twice. On day 3, we have 2 multiplied by itself 3 times. On day 4 and 5, we have 2 multiplied by itself 4 and 5 times. That's our exponent. On day 1, we have 2 to the first power, which is 2. On day 2, we have 2 to the second power, which just means 2 times 2, which is 4. And then on day 3, we have 2 to the third power, which indicates 2 times itself 3 times, which is 8, and again for 4 and 5. So now we're going to take our data from our table and fit it to this exponential growth model of y equals a times b to the x. Our x is equal to our days, and our y is equal to the number of new infections. Our a is our starting value, our y-intercept, and our b is our growth rate, our multiplier. Starting with our growth rate, we remember that the pattern is we multiply by 2. So 2 is our multiplier. Our starting value, our y-intercept, is the y value when x is equal to 0. In our table, when days are equal to 0, our x is equal to 0, the number of new infections is 1. So our starting value is 1. To see if this matches up, to see if our model matches up with our table, let's plug in days for 0 for x. So we have y is equal to 1 times 2 to the 0 power. We do exponents first, thanks to PEMDAS. 2 to the 0 power is 1. 1 times 1 is equal to 1. That matches up with our table. Let's do for day 3. Plug in 3 for x. So we have y is equal to 1 times 2 to the third power. Again, doing exponents first, we have 2 times 2 times 2, which is 8. 1 times 8 is equal to 8, and 8 is the number of new infections that we have in our table for day 3. So that lines up perfectly. Let's move on to making predictions. Scientists used exponential models to forecast the spread of COVID-19, which helped governments distribute resources and make decisions. Here we can see the CDC using different exponential models to predict the spread of COVID. So how many new infections will there be on day 10? Using our model, y is equal to 1 times 2 to the x. We can plug in 10 for x to find out y, the number of new infections. Y is equal to 1 times 2 to the 10th power. Using our calculator, we can see that 2 to the 10th power is 1,024. Y is equal to 1,024 on day 10. 10 days into the pandemic, there are 1,024 new infections per day. Optimistic estimates put the COVID-19 death rate at 1.5%, with variation based on health and age, etc. What's the expected death toll from the day 10 infections? So on day 10, we had 1,024 new infections. We can multiply this for our death rate as a decimal of 0.015 to get 15 new deaths. Predict the number of new infections on day 30, 1 month into the pandemic, and the corresponding death toll. So using our equation, y is equal to 1 times 2 to the x, we're going to plug in 30 for x, 30 days. So y is equal to 1 times 2 to the 30th power. 2 to the 30th power is this huge number, 1,073,741,824. So we have 30 days into the pandemic, a little more than 1 billion new infections per day. With these a little more than 1 billion new infections, using our death toll of 0.015, we have about 15 million deaths. The COVID-19 pandemic was devastating, with more than 4 million deaths worldwide and 600,000 in the United States. Thankfully, though, the death count never got as high as 15 million in a single day, the 15 million that we just predicted. What slowed down the virus? This leads us to our discussion. Its growth rate wasn't as high as the 2 times that we predicted in our model. Resistance spreads as people get sick and recover, but there's another important reason, and that's the flatten the curve. Flatten the curve was all over news headlines, and this was just a public health campaign to keep infections below hospital capacities. We were all encouraged to wear masks, to avoid travel, to avoid events, to wash our hands regularly so we could stop the spread and keep the number of cases below hospital capacities. Let's turn to the spread of COVID or the spread of disease in general, this is what happens when we have no public health measures. We each spread it to 2 new people. So on day 4, we have 16 cases. Those 16 people spread it to 2 new people each. We have 32 new cases on day 5. Let's say, though, after 2 days of spread, there's a mandate saying that we all have to wear masks. Everyone cancel your travel, other similar things. So on day 2, public health measures are imposed. This reduces the infection rate to 1.5, from 2 times to times 1.5. So on day 4, there are 9 new infections. And on day 5, there are 13 new infections. Here's what it looks like with no public health measures. And here's what it looks like with public health measures being imposed a few days in. So flattening the curve, enforcing this mask mandate would reduce the rate of spread from 2 times to 1.5 times. Given a death rate of 1.5%, how many lives would this save daily, a month, or 30 days into the pandemic? And note, only consider deaths from new infections on day 30. Once you finish those calculations, let's turn to a different example. In addition to masks, there were also some more controversial and restrictive government mandates during the pandemic. Here's a picture of restaurant workers in Long Beach protesting job losses from dining restrictions. Some people, due to these dining restrictions, lost their businesses and/or their livelihoods. A second discussion question is, mask wearing, an indoor dining ban, and other measures reduce the infection rate to 1.5. The government is also considering an outdoor dining ban, which would reduce the rate of infection to 1.4999. Note that these are completely hypothetical numbers, just for a thought experiment. It's almost impossible to measure the true infection rates, so these rates are just to get you thinking about public health trade-offs. Should the government also enforce an outdoor dining ban? Support your answer by calculating the lives saved by the outdoor ban on day 30. That's it for today, and we'll see you next time on Skew the Script.